Hello. Some of you may recognize me. My name's Jim, and my function is to get speakers. So I encourage any of you who have anything to say to Baypiggies, let me know. And good, I'll come run get you. Is anybody here for the Newbies Night, for the second part of Python for Programmers? Wonderful. Tonight's talk is on the Natural Language Toolkit, and it'll begin as soon as our speakers get here. There is a microphone in the back for questions. What I think will be the format is that the speakers will speak in turn, one at a time. There are 3 of them. And after that, we'll have questions. I don't know what they feel about immediate interruptions. So I hope we can follow that format as best we can. Are any of you Stephen Bird? Wonderful. Come on, step right up.
Thanks, Jim. Thank you very much for welcoming us here on the Google campus to the Baypiggies Python Interest Group. It's a great pleasure for us to present our work to this group, and we're really here just as much to tell you about what we've been doing as to get your input on Python and various new applications, and we'd be really delighted if we found some new collaborators in our open source project. So thank you very much for this opportunity. There's going to be 3 presenters tonight, starting with me, and each of us will introduce ourselves. So let me just very briefly say I'm from Australia. That's why I have a funny accent. I used to live in Philadelphia, and I still have an affiliation with the University of Pennsylvania, and I'm in the Department of Computer Science at the University of Melbourne. With my co-presenters tonight, we are at Stanford University for the Linguistic Society of America Summer Institute with about 500 people. I recognize some faces of our students here. It's great to see you here. And in fact, I expect some of these students would appreciate help with getting rides back to Stanford campus. So if anyone's going that way, please help out. And just while we're getting set up, let me remind you to ask questions as we go. We've been involved in natural language processing for a long time and maybe making assumptions. Please just interrupt. So the world is really awash with text, right? And you've probably confronted this yourself as you try to sort through news sources and blogs and I don't know, whatever it is you look at. Maybe material in other languages. But there's other things that are text too, like transcribed speech, automatically transcribed speech. There's no shortage of text around the place, and a lot of interest in indexing that text and searching it, of course, as you know. Natural language processing gives us a way to automatically process the text, to extract the structure and the content of the text, and to give people access to the information which is locked up in this text. So if you think for a moment about Wikipedia, there's a lot of knowledge in the text, but it's not really in a very structured form. There's structure in the pages, of course, but there's just free-flowing sentences in there with all this information. And how can we access that? Well, natural language processing provides the techniques to do that accessing. And we'll be saying more about what natural language processing is in more detail in just a moment when I pass to Ewan. So there's a couple of goals. One is engineering goals. So people like to build systems that process language. Maybe you want to build an automatic summarization system or translation system, question answering system of that ilk, dialogue system. Right, those have engineering goals. And then there's scientific goals. You want to understand the structure, the nature of human language, the type of variation you get, why people speak in certain ways, why authors present ideas in certain ways. So those are the scientific goals. And what's exciting about NLP is it brings the engineering and the scientific goals together in a particularly interesting way. And it all concerns data. So a big part of anything with natural language processing is handling many and varied sorts of data. So what I'd like to do is to give you a very quick whistle-stop tour of different kinds of data that we deal with. You're not going to get a full sense of what's covered by the data, but here's an example. This is from the Wall Street Journal, and every word is followed by a slash, followed by a part of speech tag, which tells you if it's a noun, a verb, or what kind of word it is. And also there's groups of words that are surrounded with square brackets. Those are noun phrases. Those are the types of entities that we might want to index and identify.
Are these on your website? These slides?
They will be. They're in our repository, and they'll be on our website. And I should say we've brought along a bunch of CD-ROM distributions of the software that includes all the documentation as well, and I'll give those out at the end. Here's an example where the text has not only been grouped into noun phrases, but into whole parsed sentences. So it's not completely transparent here, but these are actually tree structures. And they've got the words. It's deeply nested. It's completely obvious to any Lisper. They look rather like S expressions, but yeah, it's a tree. Here's another one. This is just pretty much the same information in a different format. This will be a little bit hard to see, but this shows it's a story from Associated Press Newswire, and it's talking about an event, Nairobi, Kenya, thousands of labourers, students and opposition politicians on Saturday, blah, blah, blah. And all of the named entities are tagged. So we have locations, organisations, times, people, cardinal numbers. All of these have been identified. Another one, biomedical text. It's getting smaller and smaller. This is XML. Every item has its part of speech. It's whether it's a noun or a verb identified, but then also particular genes, interactors, various other expressions are marked up specially from controlled vocabularies. So that's just a few. That's just a sample of these. Here's not a text, but a lexicon. So this has 120,000 entries telling you how to pronounce each word. And it's used by speech synthesis systems. And you'll see some lines have a 1 or a 2 near the beginning. Those show variant pronunciations of the word. Approximate, and approximate. Yeah. So one of the first goals in putting together the Natural Language Toolkit was to bring some organisation on all of this and to make it a little bit easier for people to manage data. So if someone's going to write an interface to do something with his data, they should only have to write it once and then share it, right? And actually, reading these formats is harder than you might think. Even reading something like comma-separated values is difficult. You can't just split on comma. And it's quite easy to get it wrong. So we felt it's a one-time effort to get it right. If we did get it wrong, it's a one-time effort to fix it, and let's just share all this. And the result is all this data then becomes accessible and is used for training models and doing experimentation, as we'll hear about in just a moment. The second reason is for standard algorithms. So it's actually quite difficult to get into natural language processing because it requires understanding of algorithms in computer science, artificial intelligence, search methods and so forth, machine learning, and of course linguistics. And that's a bit of a learning curve. And it turns out that the clarity of Python makes it very easy for people to just read the reference implementations and understand how things work. And I'll show you very briefly in a moment what that's like. But Python has been crucial, I believe, to our success in making the algorithms and methods and data structures accessible to a diverse audience. A third motivation in developing Natural Language Toolkit is to provide educational materials. So currently this has actually almost reached the stage of a complete book. It's 380 pages, and we hope to finish it up in a matter of weeks. A consequence of this is that we've managed to consolidate a lot of the core knowledge that people need in order to do natural language processing. The authors have been doing Python teaching for 5 to 7 years at least, and have got a lot of experience there, but we've had to be very selective in what we want to present to people. What features of the Python language are particularly useful for work in this area? And I'll show you in a moment as an example. A key aspect of our approach is that people could learn by doing. And so all the materials are highly interactive, and one of the things I'd be just delighted if people went away and did is try some of the examples in our book where you just type them in, try them out, and start modifying them. It's been a great way for people to learn Python who actually have no prior interest in Python. Right? They only heard about Python because they're interested in this application, and then they got into programming Python and are using it for other things as well. Not only is it practical, but it's theoretically well-founded. So the authors are academics, and we publish in the academic literature, and we're very interested in making that literature accessible to a wide audience. So the book is supposed to be a stepping stone. And although you'll see an algorithm implemented in the toolkit, it's not going to be a highly optimized algorithm. You'll understand how parsing works, but then you'll want to go to the algorithms in the literature and learn how to do it in a more optimized fashion. So, like I mentioned, there's a book. There's also 50,000 lines of code, which is thoroughly documented, and 300 megabytes of data sets. And that's all under open source license. So let me just explain briefly how we got started. It was probably back in about 2000 when I was teaching at Penn and decided I'd had enough of teaching in Perl. I could never understand never understand what I even wrote, let alone what the students wrote. And of course, the formatting that you got in from students was all varied, and Python just sort of dictated that. Anyway, I don't need to evangelize Python here, but I just decided 2 weeks before I began teaching in 2000, I'm going to learn this language and teach it. And it was a little bit rough, but it was actually very fun. And as the language has developed, we've found that some of the things we had to implement manually, for instance, implementing sets using dictionaries, just came along. Implementing a kind of default dictionary, that just came along. Implementing trees, that just came along with element tree. You know, there's a whole range of things there where we kind of seem to dovetail with the development of the language, and we're just delighted to see how that's worked out. So anyway, the language NLTK got quite over-engineered. We started to, with all these different kinds of data, we decided to have a blackboard model where you could basically continue to add layers of information over on top of the basic data. So you could take a text, identify categories of the words, and keep adding more and more information. And eventually, we found that our programmers were programming in NLTK, not programming in Python. Our interfaces and APIs became so demanding that you just spent your whole time looking up the help information and not learning Python. So we abandoned that and re-implemented everything 2 years ago, and that's been called NLTK Lite. It's now at version 0.8, and when it hits version 1.0 later this year, we're going to make that NLTK 2.0, and then we're going to be much more conservative about changing the interfaces. So now it's a little bit fluid, and we're trying to get the interfaces right. And so that's particularly why we're keen to get input to the development. I want to just give you a quick example of the way we've been teaching Python. So suppose we want to count the 20 most frequent words in a text. Here on the top 5 lines, we define a default dictionary which, when it has no entries, defaults to an int, which is going to give us a 0 value if we just increment. So, for instance, in our second line, after we split the text on white space, we're just going to be iterating around counting the words. And then at the end, we can do a reversed sort of the words by their frequency. And that's already quite impressive that we can do that in 5 lines, and it's pretty readable. But because counting words and frequencies and sorting is so important in natural language processing, we've just created this class called FreqDist, frequency distribution, which does that for us, and we can do exactly the same functionality in this single line. Moreover, we use our own tokenizer, which does something much cleverer than tokenize on white space, which turns out to be a rather bad idea. So at this point, I'll pause if there's any questions, and then I'll pass to my next presenter, Ewan Klein. Yep.
When you're talking about word splitting, that's somewhat Eurocentric. How do you handle word splitting in Asian languages that don't use spaces?
So the question...
That even have words joined together in a single content.
So the question is that splitting words is a rather Eurocentric idea. It's actually, the Roman writing system, and how do we deal with the situation of languages where the words aren't split apart? So, in fact, I'm glad that was mentioned, because one of the major activities within computational linguistics, a close relative to natural language processing, is analysing the words of different languages and how we can actually do that splitting. And so there's a lot of work. There's two methods, essentially. You can collect a list of all of the words, and you greedily search for the word in the prefix of what you haven't yet analysed, and that's fairly reliable. But for languages which have very productive word formation rules, that's not enough. And so they develop very powerful statistical methods for that. But that's one of the major application areas of this technology. Yeah.
Languages evolve and mutate. I mean, I can't even understand Shakespeare. How do you handle all the different versions of English?
So how do we handle all the different versions of English when language is evolving through time? Well, one of the interesting things we can do is to get collections of data from previous versions of English. So the collection of Middle English data is complete, right? Nobody is creating new Middle English. The same with Old English. So these have all been digitized and annotated, and you can actually systematically study the evolution of English over time by writing programs. So that's how we...
Regionally, because the people who wrote in the English Midlands had a different language from Chaucer.
Yes, so there's regional varieties, and in fact another approach to this is to study that systematically. One of the databases that we're looking at in our course at Stanford right now has 10 dialect regions from the United States, and we can actually look at how the pronunciation of vowels changes over space and time. If there's no more questions, let me pass on to Ewan.
Hi, my name is Ewan Klein. I'm on the faculty at University of Edinburgh. I'm just here for the summer. And I'm going to give you a very broad brushstroke view of natural language processing. So broadly speaking, if you look at the mass of activity in natural language processing, you see three major areas. First area, people are looking at ways of understanding natural language or capturing what's involved in understanding natural language. What's the meaning? How do you get at the semantics? The second area of enormous interest is how do you translate from one language to another, from English to Chinese or from Arabic to Greek. A third area is, given that you have some representation of content, of meaning already, or some data, how do you express that in natural language? So how do you take, for example, a series of numbers about weather and package that up into a message that is intelligible and grammatical and coherent to the listener or the reader? Now, there's other areas of natural language processing, but these are probably ones which you're most likely to encounter. And within NLTK, although there isn't a theoretical bias, in practice we've tended to look more at technologies which feed into the understanding area. We can also consider different modalities in which communication takes place. Stephen has said a fair amount about text. He's also mentioned speech. We couldn't do without speech. And of course, it's worth mentioning that often we have language intermingled with images of various kinds. And again, within NLTK, we've tended to focus primarily on text. Of course, you can turn speech into text by carrying out speech recognition, but we've only looked at things after that transcription, after that turning into text has taken place. So we're not involved with speech processing. And I want to give you an example which is not exactly typical, but it encapsulates some interesting aspects of language. All of you know a lot about language. You'll have strong views about it, no doubt. And you probably have views about this data. This is a... Let me just give a little bit of context, a little background to this enterprise, which is a lot of work in natural language processing tended to take place in a rather haphazard, individualistic way that was difficult to benchmark. And the US Defense Advanced Research Agency, DARPA, instituted a sort of social practice which involved bringing together a group of people to work on a common task. They would have a common target in terms of achievements, and they'd have common data of the kind that Stephen mentioned on which to work, and they would have systems which would compete to get results on that common data. And the nice thing that the DARPA project manager could show was, over here performance was down here, but next year it was up here, and you had this nice rising curve to show that you're a good project manager and you're making progress. And although one can laugh a bit about that, actually it has been generally very productive. So this data here is one of the more recent data sets which has been adopted by the community as a challenge. People are competing to deal with it. What they're trying to do is, let me give the next sentence. Supposing you want to know if this sentence, Alberto Tomba won a race, is true or not, question is it plausible this is true given this text? That's the way to think about this. I mean, you can also say, well, can you reasonably infer the hypothesis from the text? And this is meant to capture not some logical notion of reasoning, not something like first-order theorem proving, but something much closer to what humans do, which is more to do with plausibility and more diffuse in many ways and much harder to pin down. Sorry, there's a couple of questions here.
Mine is more of a comment, but the coincidence is too strong for me to be quiet, because I am a Bolognese quadrangle. Alberto Tomba comes from Castelnicusi, which is where my grandfather's farm was in the mountains, 20 miles away from Bologna. Sorry, I just couldn't let it.
Well, I stand corrected. I will write to the organisers and give me the details and I'll tell them.
I'm sure some journalist wrote that, and that
Yep.
journalist was lying.
Well, certainly deeply mistaken.
If he was from near Bologna, then
20 miles, but it's the mountains. Yeah.
yeah, but
It matters in Italy.
I know. I know people who come to the United States and got caught on this. We're in San Francisco. Well, why don't we just go over to New York and
So,
they can be speaking a different language.
ex-colleague of mine tried actually to solve this problem using first-order theorem proving, and the kind of problem that he hit was his theorem prover didn't know that capturing a gold medal meant winning a race. It's kind of knowledge that we all take for granted, but it's common sense knowledge, and as you probably can realize, it's very hard to regiment and to capture that kind of... maybe. Capturing, you can... Yeah, there's lots of... Language is generally fairly vague. It involves metaphor, it involves hyperbole, it involves implicatures, all kinds of things. So it's difficult. And the question is, how well can we get machines to do this task? So we have pairs of texts and hypotheses like this. The texts are ones which are naturally occurring in some sense. The hypotheses were created, and the data, the training data says, it gives a true or a false label. So either this follows or it doesn't. In this case, this is meant to follow. I'll give you another example.
So, sorry, this is really hard because capturing a gold medal might be winning a shootout or a jump. It's only, you have to know that the Calgary Olympics were Winter Olympics, and there all the medals you can win are for racing in one way or another.
It is difficult. It is a difficult task, but it seems to be one which is a reasonable challenge for natural language processing technology. I'm not saying that we can do it, but it's the kind of thing that we're making progress on, and I want to use it to motivate some of the techniques we'll talk about later on. Within NLTK, no, we can't solve this, but we have tools that get you some... If this is like, talking about skiing, this is the mountain, we'll get you into the foothills at least. So this is another example. Again, this hypothesis is meant to follow, and you could note here that this is actually quite hedged in the sense that it says that may be doing a lot more, apparently can reduce. And the claim is that we still think it's fairly plausible that we can treat this coffee drinking has health benefits as supported by the text.
But it's not a simple 0, 1.
Oh, sorry. I'm distracted by the fact that I thought this blah's got eliminated from this slide, but apparently not. There's another question there at the back. Okay, to repeat the question, there's lots of information, rich information in spoken language, which is absent from written text. So are we in fact setting the hurdle too high for ourselves by looking at text? And I think in some sense the answer may be yes. On the other hand, we do have huge amounts of text out there, and if we can make some progress towards extracting meaning out of it, it's still going to be a win. I would say, though, that within more theoretically oriented approaches to meaning, looking at dialogue is an area of huge interest. Why? Because you can isolate much more clearly how meaning emerges from social interaction and expectations of hearers. So there's some really interesting issues there about what's shared ground, how you can derive more than is strictly said. But yes, and it's true that without looking at those dialogue aspects, we're somewhat handicapped. But we just have such a huge amount of text, it seems perverse not to try and study it. So information extraction, okay, these are things which people are doing. All these, sorry about this. I have 3 blahs and something else. Oh, no, kabar. Question answering is meant to be the next thing after information retrieval. Rather than typing in some keywords, the claim is that you could ask a specific question and get back a short sentence or passage which would answer your question. So you might ask, who won races at the Calgary Olympics?
That's not a short list. But the UI could deal with that
This is a more sophisticated. Okay, the typical question answering question is, who was the first man on the moon, for example? Who was the first astronaut to land on the moon? Well, you're right, there's one sentence. In this case, you'd have to give a list, and so you have to be a bit more clever. So you're quite right. But the point here is that if we had that way of drawing inferences that I mentioned in the textual inference, that would help in that task. Information extraction, broadly speaking, is trying to get structured data, for example, like relational tables, out of unstructured data like text. It's a big area in biomedical text mining, where we have masses of biomedical texts online, research results, more than any human could. I mean, there's just no way you can keep up with it. Trying, for example, to look at something like, this is a protein, they're interacting. That's the kind of task which information extraction tries to address. And again, having some notion of inference would help that in many cases. Spoken dialogue, we've already mentioned briefly. Text summarization is trying to distill a long text into a short one. And to a certain extent, these things I call hypotheses go some way towards that distillation. So this is, I say, extremely... oh dear, this isn't the most recent version, Stephen. We had an SVN problem here. Let me improvise a bit. So what can we do? What kind of tools do we have in our armory to deal with something like the textual inference? Well, one thing you might think of that's easy is you just look at the bag of words for the text and see how much that overlaps with the bag of words in the hypothesis. And that actually does, as a kind of baseline, surprisingly well. But if we think about that first example, what was the guy's name? Alberto Tomba. If you said something like, he almost captured 2 gold medals, that certainly doesn't imply that he actually did capture them. So that's just one word, but it makes a huge difference. Or he failed to capture. So it seems as though, in some cases at least, you need to do more than just looking at bag of words. So the next thing that people have tried to do is look at the structure of those texts and the structure of the hypothesis, and in particular try to get more idea of some simple aspects of meaning from looking at those structural correspondences. Sorry, there was a couple of questions.
And yet, if you said he almost captured both gold medals, then you would be somewhat implying that perhaps he really did capture one.
Yeah, that's true. And that's another example of where language has quite intricate kind of inferences. Another thing it's hard to do. I think... Okay, very good.
No, it's supposed to be ski racing, not free diving.
Sorry, there's another question?
Yes, I have trouble extracting meaning from some English, for example, political speeches. How does your program
Let me hasten to say, I do not have a program that extracts meaning from free text. What we have are, it's like, okay, you're trying to build some complicated machine, and you have various tools to do that, and maybe you don't get all the way. You want to build a Rolls Royce, and you end up building a motorbike, yeah? And we're kind of at the motorbike stage at the moment. So, next one. Okay, so we can look for structure, and that actually helps more than you might expect. And that essentially is building something like the parse tree that Stephen illustrated earlier on. We can have rules that do some degree of semantic inference using aspects of logic. They tend to be very hard to use. We can try to have a much looser notion of paraphrase, that these 2 words or these 2 phrases mean roughly the same thing. And there are kind of clever ways in which you can try to capture or approximate that. And Ed was going to say something a bit about looking at word similarity or an aspect of word similarity later on. And of course, you need to be able to have some way of representing background knowledge, possibly ontological knowledge, but you need a big collection of facts that you can somehow access. And that's a kind of bootstrapping problem because a lot of that background knowledge is available as text. If we could understand text, then we could extract the background knowledge, which we need to understand text. So we can kind of try to get a bootstrapping going there. Yeah?
So we have background knowledge, so it might be reasonable to expect some future version to be able to tell the difference between Bob's as smart as Einstein, Bob's as smart as it is. But what about something where there's like, where humans expect to understand and it's not meant to be taken literally, like you feed a logic proposal into this thing, will it come out with the hypothesis that babies are really succeeding?
I'm not sure. So you're saying that a human would realize that inference shouldn't follow?
Yes.
It's a satire, and a machine recognizes that it's a satire, and not attempt to conclude from what it says that this is meant to happen.
Often human beings fail to.
Well, of course.
Again, this is an area of very active theoretical research. It's nowhere near to being deployable on a large scale. It's still, people are trying to build adequate theoretical models. One thing you might say about these text hypotheses pairs is maybe you could just get a very powerful machine learner which would look at the cases which are marked as following, cases which are marked as not following, extract some features from that and build a good model. In practice, that doesn't work either. It seems as though you'd need a really humongous amount of data that was human annotated to do that efficiently, or do it effectively rather, with machine learning. So this is an area where it seems that you really need to have some statistical, some machine learning knowledge, but you need a lot of other knowledge about language as well. So I'm just going to
Get it to where it could learn from as much language as a child needs.
that's again something which is people are working on that. I think, in fact, there's a Japanese group that claims to have a system that has the same knowledge as a 10-year-old child. I haven't verified this myself, but it's, again, a active research area to try to give computers kind of input that would allow them to learn. I think that's still very much a research topic. I need to stop, really. Just very briefly, lots of challenges. One important thing to note in the field is that parsers, things which take strings as input and give back your syntactic structure, are becoming much, much better, much more broad coverage, more robust, and they're almost reaching what one might call commodity status in the sense that every reasonable research group should have one, which wasn't true even 3 or 4 years ago. And finally, some aspects of natural language processing, I believe now, it's fair to say, are moving out of the research lab and into the real world. And we have evidence of this all around us in the Bay Area.
So, I'm Edward Loper. I am in the final year of my PhD at the University of Pennsylvania. And long ago, Stephen and I... Oh, yeah, can you... yeah, that's fine, yeah. I was a TA in Stephen's class, I guess, when we started this NLTK package. It was originally designed basically to be an educational tool, but it's been growing ever since. So what I'm going to do is basically run through 3 quick examples, just showing you what it's like to use NLTK and what sort of things you can do with it. As Ewan was saying, NLTK isn't going to answer any of these big questions like extracting meaning for text for you, but it will provide you with some useful tools to process text if you want to do sort of simpler, small tasks. And it'll help you to learn sort of what techniques you need to use and what sort of processing you need to do to text to get it to work. So is this plugged in?
Yep.
So One thing that I'm going to talk about is classification, which is a very sort of general idea you'll encounter in machine learning. But the idea is that we have some sort of object, a piece of text or a word or something, and we want to assign labels to it. We want to decide whether one of our emails is spam or not. We want to know what the subject of a document is. We want to know if we've got a word, often words are ambiguous, we want to know which sense of the word is getting used. All right, so let's look at how we can do text classification. So one thing to know about text classification is that in order to do it, you really need to come up with a way of telling the computer what aspects of the thing you're looking at are important. And so this is talked about in terms of features. So a feature is basically some aspect of the object that you think is important, and you need to basically let the computer know what those are. And generally, the features are defined manually what they are and then automatically extracted. And then these are given to some sort of machine learning system or some other type of system, which then tries to figure out how to go from those features to an appropriate label. All right, so this is just giving a quick look at what classification is like in NLTK. So at the top here, we've got a classifier that we've already built. And this is just showing how you store features when you give them to a classifier. So basically, features are just dictionaries, mapping from a name of a feature to some value of that feature. So in this example, I guess we're classifying animals. And here we've got an animal that has fur, that's got some fur, it's got 4 legs, it's large, and it has spots. And so our classifier, when we use this classify method, will just pick what it thinks is the most likely label for that, and here it'll say leopard. You can also ask them what it thinks the probability of different labels is, so you can get some idea of how sure it is of whether that's correct or whether something else might be correct. Typically, in order to build these feature structures, you're going to define some sort of feature extractor function, which just takes whatever the object you're interested in is and maps it to a dictionary. And that's where a lot of the work that you'll be doing would be, is sort of defining that function and what exactly should go in there. So here's a very simple feature extractor for document classification, which just defines a feature for every word in the language that's true if that word is somewhere in the document. All right? And so the classifier can then learn that, news documents tend to contain words like war and, country names and things like that. Sports documents probably contain names of different teams, things like that. And it can use those features to figure out what labels should be assigned. All right. So now I'm going to switch over to a demo here. All right. So here we're doing the task of guessing the gender of a name that we've never seen before. So one of the many corpora that's included with NLTK is a large list of names identified as male and female, with some overlap between them because some names can be used for both. And so we can use that as training data and try and build a classifier that will guess what the gender of a name is. All right? So if we start out here with just an empty feature set, we can build a classifier. It won't have anything to go on. Basically, we just say, I have a name. I'm not going to tell you anything about it. What gender do you think it is? And so it looks at the training data. It finds out, well, female names happen more often than male names, so it just always guesses that things are female. All right? So here, this is the probabilities it's associating. It's saying, well, I think this name is 66% chance it's female, 33% chance it's male. And it's getting, about 60% right. Okay? But we can add more features. So what do you think would be a good feature if you've got a name to try and tell what gender it is? Anything? One at a time. Yeah. Ending in a vowel. All right. We'll include Y. All right. So now we run it, and we're doing a little bit better. We're getting about 75% right. So actually, that was a pretty useful feature. And you can see it's still most of the time guessing for anything that doesn't end in a vowel that's 60% male, 40% female. But when it does end in a vowel, it's much more likely to be female. All right. Any other suggested features? Monosyllable or polysyllable?
Yeah.
Well, so that's a little hard for me to do, so I'll do something a little bit simpler. Let's just look at how long the name is. All right. And so now we're up to around 75%, and you can see it's getting more of a distribution. It's getting a good number of them right. And we can, go ahead and add a bunch more features, say, a feature saying whether it has each letter. And as you can see, you can keep adding this type of feature. So this is basically, though, you should get an idea now of what it's like to try and build a classifier for something. The classification algorithms are already there, and if you're doing this type of thing, a lot of the sort of fun work is just trying to figure out what the interesting features are to guess it. Yeah?
Is there possible future work to refactor this so that the machine learning part can be separate? This is definitely for text processing, but a lot of it are base classifier and LE and all
Mm-hmm.
other stuff. Is it possible for future refactoring, or are you guys using something like SciPy?
So the classifiers that are actually implemented within NLTK are all fairly slow, and you're not going to want to use them on huge data sets. Because we want these things to be accessible, we want people to be able to learn how these algorithms work, so they're written in Python. And if you're doing lots of intensive numeric processing, Python might not be your language of choice. For that reason, we've been working recently, actually, on basically adding the ability to call into other machine learning packages that are out there, like Weka and Mallet and these other sort of standard machine learning packages, so that once you get your code up like this, using that same interface, so the interface is always just going to be a dictionary from feature names to feature values, you can plug in whatever classifier you want. All right. Now let me switch to another example here. So here I'm going to look at the question of when two words are similar. And this is an interesting question for a number of tasks. If you're doing search, for example, you might not just want to search for that one word that you typed in. You might want it to find other words that are similar. If you're doing question answering, again, you might want it to try out different paraphrases of what you said. Knowing what words are similar also can be useful for trying to do things like find the structure of a sentence, because if you know what words act similarly, then you might be able to sort of share training data between them rather than modeling everything separately. All right. And it turns out there's different sort of meanings you can have when you say, are two words similar? So this example is looking at one of those, which is what words occur in similar contexts. And so here we have a function which basically just builds up a map, reading from the Brown corpus, which is a standard corpus that's already got some information in it. Just going through all of the words right here. So this is this line here is lowercasing all the words. And then we go through each word, and we look at the previous word and the next word, and we build this map, this dictionary that tells us for each word what are the previous and next words that appears next to. All right. And once we've built that map, we can use it to decide whether two words appear in similar contexts. So here's a function which takes the context map that we just built and a word, and basically it's going to use a frequency distribution, which you saw earlier. It's basically a histogram. It counts things up. It makes counting and doing some sort of numeric or some statistics pretty easy. And here we're just counting up how many times if we look at a new word, how many times that word appears in the same context as the word that we already have. All right, and that'll give us this frequency distribution. We can then sort it and then see what the highest ranked things are, and those will be the ones that appear in the same context most often. So, and then here at the bottom, just running it on some random words. Man appears in similar context to it, he, there, this, however. Woman to man, number, world. Walk appears similarly to be, do, go. In appears in context similar to of, to, on. So you can see here, even though we actually haven't given it anything like parts of speech, it's inferring something like them, right? So this actually gives some justification to the notion of part of speech that these things really do act in similar ways. All right, so skipping right on ahead. So another notion of word similarity is looking at what words just occur near each other. All right, so this function, I'm not going to go through it in much detail because of time, but basically this function is going through for each document in that corpus. If it's a noun, it looks for any other nouns that are nearby, and it's going to add that into a frequency distribution, which is this histogram object. All right, and then once we've built that association thing, we can just ask it for a given word, what's the most likely word to appear in its context. So basically this gives us something like free association. All right, and so if we ask it, what does man appear near woman? What does woman appear near world? Level AF. I don't know what AF is. And that's pure coincidence. This corpus was built long before the Python language even existed. So different meaning of Python, different meaning of exception. All right. The last thing I wanted to show real quick, let's see how this works, is a graphical demo that we have for parsing. And so parsing is basically the task of figuring out the structure of a sentence. And that can be useful when you're trying to do some deep processing like you would need to do for the type of inference task that Ewan was talking about. So in that case, you really want to know sort of what the pieces of the sentence are and how they fit together, right? Because then you can tell, if you've got a verb and then a subject way over here, object over there, how they relate to one another. All right. Perfect. All right. And so I'm not going to go through a very detailed explanation again, but basically this is a demonstration of a parsing algorithm or a class of parsing algorithms known as chart parsing, which basically uses a dynamic programming approach to incrementally try and figure out what the pieces could be and then put them together. And it's using dynamic programming so it doesn't have to recalculate those pieces again and again. And so we'll use Early's algorithm here. And basically, it's going to just start positing some trees. It says, well, there might be a sentence that starts here and has a noun phrase and a verb phrase. Or we might have a noun phrase at the beginning. And it's just going to posit a bunch of things. Eventually, it'll find one that actually matches with a text, right? And so now it knows there's a noun phrase there, and it can go in and fill that in. So here, the dotted lines before, we're saying there might be one here, this tree structure. We found that left part, and now we know that we should go ahead and look for that right part. And so I'll just run this on through. And you can see it's checking a whole bunch of different constituents, slowly building things up. And it turns out that even for very simple parsing, you get a lot of ambiguity and ambiguity in some unexpected places. So it actually turns out that this sentence, John ate the cake on the table, is ambiguous, all right? with one meaning where, we'll do this meaning first, where the cake is on the table, and another meaning where the eating happened on the table. So John is sitting on top of the table. And it's not that problematic if your sentences are, 5, 6 words long. Once you get into sentences like you find in the real world that are 30, 40 words long or longer, with many, many prepositional phrases that can attach to different places, you get an exponential blow-up of the number of possible parsers, which is why this task is pretty hard. Yeah?
Does it take into account punctuation?
So this one is not. So that's going to come down to basically how you define your grammar and how you do your tokenization of your leaves. So a parser is going to need two things in order to try and figure out what a sentence's structure is. It's going to need the input, which will be a list of words. In this case, I didn't include any punctuation, but you could have one that does. And it'll need a grammar that says how pieces can be put together. And if your grammar includes punctuation, then it'll use it. And most real-world grammars do. And in fact, when you're doing this in the real world, as I said, sentences will have hundreds of thousands of parsers, so you need to use probabilistic methods and find the most likely parse. All right. So that's the last demo I wanted to do. And now I think if we have time, I'd like to open it up to questions. Oh, but you had, or should I? Okay, yeah.
Do you have a metric for how well your parsing works on a set of text? So you can say, I can understand this text, and I cannot understand that as well?
Well, so it's an interesting question. The question is how well, if we have a metric for how well the parsing does. And there certainly are standard metrics to evaluate that. We don't actually provide a full grammar parser that will parse unrestricted text. There are several of those out there, but doing that in Python just isn't practical, basically. And as I said, they generally have to be statistical systems. Building a grammar that will create the correct parse for any tree is easy. The hard part is making sure it doesn't also generate a million other incorrect parses for the same tree. And so for that, there are, as I said, a number of standard parsers out there. There's Collins parser, and I could give you references. But basically, they all do this sort of probabilistic thing. They're all trained on, generally speaking, the same corpus, which is this 1 million word corpus called the Penn Tree Bank, which is manually annotated with trees. And then they just automatically try and learn how to construct those trees themselves. Yeah?
So I'm trying to understand the data structure a little bit. It looks like words are parsed with nodes, and the nodes have metadata associated with them based on what kind of words that they are. And then that infers how they associate with other nodes.
When you're doing parsing, you mean?
Yeah. And the data structure you get back from it. And then those are laid out in a hierarchy.
So the data structure that's an input to the parser is just a list of strings. All right. You could also have it be a list of part of speech tags if you wanted to do grammar. Sometimes people will do part of speech tagging first and then do parsing just on that. Or you could have it be a list of, there's different data structures you could use. The data structure you get back is a tree data structure that's basically a class we defined. I mean, you could just use something simple. We looked into using something standard, like each element tree came in recently, but that's not really practical for this sort of thing. It's more practical for XML, because in these types of trees, we actually do want to be able to include rich information in the nodes and in various places. So one of the parsers that's included is actually a feature-based parser, where the nodes can include features saying this not only is a noun phrase, but it's a noun phrase that's masculine and is in the dative case or something, so that it can use that information as it builds up the tree.
Is there a way for a node in the tree to refer to somewhere else in the hierarchy that may not be inside of it?
In our tree structure, no. In the trees that you get out of any statistical parser you use, also, they're just sort of simple trees. Linguists, when they talk about trees, often have all sorts of arrows going around in them saying that, well, sure, this is up here when we say it out loud, but really it came from down here, and that there's some empty element here that you don't say, but that really has a meaning.
Well, the simplest would just be pronoun references.
Yeah. All right. Do you want to pass over to you?
So I just want to open it up now to any broader questions about Natural Language Toolkit, and to draw your attention to ways in which you might get involved. In particular, we're very keen to hear about what you want, what sorts of components you'd be interested in having, or what kind of technologies you'd be able to do that. And just before opening it up, I wanted to invite Stuart Robinson, who's one of the contributors, who happens to be in the audience, who's from PowerSet, just to come to the mic and say why he got involved as a contributor. And while he comes up, there's a mic, if you can get to it. And also to recognise Joshua Ritterman in the front here, who's from Apple, who's just helped us in the past week with packaging NLTK for Mac. So those are a couple of contributors in the audience I wanted to recognise, and then open it up to others to find out how you might like to contribute or what you'd like to see. Thanks.
Is this working? Yeah. Thanks, Steve. I got involved in the Natural Language Toolkit a few years ago. I was doing fieldwork in Papua New Guinea, and I had sort of a large collection of texts and a lexicon for the language that I was studying, and I had written some stuff in Perl to process it. At the time I was learning Python, and I found out about the NLTK, and Steve sent out an email saying, hey, it would be great if someone would write something to process text in this particular sort of format that I was using, which is a fairly widely used one because it's a program that a lot of field workers use. So I said, okay, sure, I'll do this, and got involved, and ended up, getting another person involved, Greg Aumann from the Summer Institute of Linguistics, and gradually it became part of the Natural Language Toolkit itself, and I think other people are using it. I hope. But the idea was basically, I'd written this stuff, and a lot of people were reinventing the wheel, and a lot of people were writing their own, rolling their own, as it were, solutions to parsing this stuff, and it seemed like a good idea to have it all in one place where everyone could share it and use it, and not be reinventing the wheel continuously.
Thank you.
Thanks, Steve.
So any other comments or questions? Is this downloadable? Yes, nltk.org here, and I've got some CDs at the front if you don't have web access right here. Should be surprising. Yes?
Do you know of, or can you think of any applications for NLTK for processing technical mailing lists?
So can I think of any applications for processing technical mailing lists? Sure. So one of them is automatic topic detection. What is the topic of this mail? Or if you want to put mail automatically into folders, it might be some very complex. So for instance, you might routinely just have created a folder of stuff that interests you, and it's a bit of a mixture of stuff, and you could train a classifier on that, and it would have a good chance of giving you other things of interest.
How long would that take to run, realistically?
How long that take? I mean, in the worst case, you might be looking at a few minutes to train, and then once it's a trained model, then you'd just be running it as messages came in. And maybe it's going to take a fraction of a second per message. It'll slow it down briefly coming into you, but, nothing at all. There's one in the middle. Oh, yep.
So in terms of contributing, all of you have repeatedly mentioned how good it is to have things in pure Python for didactics, but then couple sentences later how this is limited because it's too slow. Would you accept interface compatible Python callable extensions implementing some of this, if like in Pyrex or C? And if so, do you have a list of the 10 most wanted pieces that would speed things up a lot?
Okay. So there's a lot of questions. Let me just respond briefly. So this is all in pure Python because of our educational goals, but there's some problems for efficiency. Would we accept contributions using Pyrex, Psycho, or other C code, for instance. Our main concern with any of that, of course we accept all contributions gratefully, but is the distribution issues cross-platform. But if we can solve that, then we would be interested. We always want to have a basic reference implementation that anyone can read. But if there's more implementations that are more optimized, that are based on latest results in the literature, that's just great to have too.
Do you have any?
Oh, we've got a... Yes, so in fact, Edward, can you find it? We have a list linked here called nltk.org index.php/development, where we've got about a dozen of the tasks that we would really like done. So that'd be the place to look. If you're thinking about contributing, there's all sorts of ways in which you might contribute. We'd also love a logo, if anyone's a good graphic designer. Yes, at the back?
Has anybody experimented with using this for languages that aren't natural? Like if you wanted to throw together, like you're making a new mini language for a config file or something like that, and it's got this automatic parsing that you get for free, it seems.
Yes, in fact, some people in Melbourne have been using it just to parse and interpret some simple programming languages that they made up.
And does it uses the English kind of grammar rules to determine what?
Yeah, it's just context-free grammar, or BNF, that people are familiar with in compilers.
Okay.
Yeah. So.
Thanks.
That leads to another question. You've talked a little bit about using it on a range of natural languages. What actually has been tried?
So we have some data sets in here for Spanish, Dutch, Chinese, what else? Not Ebonics. There's, for every large language, language with more than 100 million speakers, there is intense interest in building automatic language processing. So that's Arabic is a big one. Hindi is a very big one. India has 400 and something languages and dozens of languages that are in the focus of automatic natural language processing. So this is exploding outside of English. And many of the same methods carry over. All of the things we said just apply transparently. And in fact, all of the data sets are just being mimicked in these other languages.
So actually, eventually this could be applied to text-to-speech or translation types of applications.
I'll give someone else a turn.
The toolkit itself, you mean?
Yeah.
Yeah. So our vision for the toolkit is that it will continue growing as more people contribute to it, to encompass any sort of natural language processing task. And we're certainly interested in adding more data sets too. So we certainly are interested in having that type of stuff added. Yeah.
Okay. Now for on the wish list. One of the most powerful methods of dealing with illiteracy in India is called same-language captioning of movies. A combination of natural language processing with text-to-speech would make it possible for people to have any text in their language read to them, and they could work with that to learn to read it.
Yeah, that's an interesting idea. Yeah. Yeah.
Was the chart parsing demo written in Python?
Yes. It's
So we used tkinter. We've also done programming using QtPy, PyQt, and GTK+, and it'd be really nice to have a easy-to-use cross-platform GUI. And we'd also love some help just on adding more demos. So, for instance, our top task there, WordNet browser, would be a graphical interface to this fascinating network of 100 and something thousand nodes, all of the words of English, and all of the relationships between the words. Just connected, richly interconnected. And to be able to explore that in a multi-dimensional graphical space would be just fascinating.
Have you considered importing that into a mind mapping program?
Yes, once we've done that, then we could put it into a mind mapping program. Yeah, sure. Yeah.
It's just links.
Yep. No, we haven't, but yes.
Yeah.
Sure.
Have you tried this for spam classification?
We haven't tried this for spam classification, no, but we should. Yeah.
A lot of data sets available.
It's just, yeah, absolutely. We gave the illustration with names just because it's a less obvious one, and many people have spam classifiers in their emails, but what about having a subject classifier built in? You know, there's a lot of classifiers that would be perhaps more useful. Well, it would be interesting now that spam is sort of there.
2 free topics.
We've got to wrap up in a minute. Yeah.
So first of all, does it support Unicode?
Well, as you know, Python is Unicode safe. The only problem.
The second question would be, is it IPA friendly? So in linguistics, you talk about natural classes when you're talking about phonetics. You talk about sonorants or nasals or vowels. So is it easy to define feature or classify feature as being, for instance, nasal or sonant? Or before we had the example of names, we said, well, yeah, how would the vowels at the end of words and actually practically is the vowel. So if we had it transcribed in IPA format, would we be able to easily say 50 words and then end in vowel?
One of the example data sets that we showed you, the CMU Pronunciation Dictionary, has pronunciation strings that are a transliteration of the International Phonetic Alphabet. As you know, Unicode has IPA, and Unicode has all these character properties, and you can have regular expressions over the character properties rather than the individual characters. It's just possibly via that method or a simple pre-processing step to have all of the natural classes of sounds that you need for the phonetic analysis. It just may be one step of pre-processing before your regular expression. But we should do that. Last question? Well, thank you very much for the opportunity to come before you. We would love to hear from you, talk to you individually afterwards. Hopefully you can figure out from nltk.org how to reach us. So if there's any way in which you'd like to be involved that hasn't been touched on tonight, please don't hesitate to get in touch. Okay, thank you.
Thank you. The Baypiggies meeting is almost not quite over. We have a mapping time now, and the most important thing I can think of is those of you who need rides, please raise your hand. Let us know. Do you need a ride? Where are you going to? Everybody's covered?
I can take 2 people to stand.
Anybody else need rides? Sure, meet at the front at the end. Does anyone have announcements?
JJ had a baby.
JJ had a baby, yes. Yeah, well, check the gender on that. Next month, our topic is the Newbies Night, and that will be the part 2 of Alex Martelli's Python for Programmers, which we deferred in favor of this month. Any last thoughts? Yes?
There was one thing, Jim. OSCON's coming up next month.
Oh, yes.
One of the things is Jeff Rush, the Python advocacy coordinator, he can't make the OSCON. So we're trying to see if we can organize some advocacy efforts as a grassroots thing. If anybody's going up there and is interested in getting involved. I set up a birds of the feather session on Monday after the tutorial.
Hang on.
Kind of out on a limb here. I'm sorry. I don't know how much everybody heard, so I'll just quickly review that. For OSCON next month, the Python advocacy coordinator, Jeff Rush, can't make the conference. So we're trying to do some more grassroots advocacy efforts during the conference. And I set up a Birds of a Feather on Monday, I think it's the 23rd, on Monday evening after the tutorials, to see if I can get a few people together to do some planning for what efforts we could, what we could accomplish during the conference. In Portland, yes, absolutely in Portland. So if anybody's going to OSCON and is interested in getting involved, either come to the Birds of a Feather or get in touch with me, and I'd be glad to do some planning in advance.
If I'm not mistaken, several days ago in the mailing list, I also noticed there is a interest in the Linux World Bird of Feathers. I don't know how that one is going because I would like to help, but where's the person responsible? Oh, okay.
Thank you. I've signed up to do a Birds of a Feather on one laptop per child. As you know, or you should know, the Sugar user interface is built almost entirely in Python. Some of the work was done here at Google Summer of Code. It's continuing all over the country, all over the world. So I'd love to have any of you who are interested in that show up and help out the crowd on the Python aspects. We're also looking for people to help out in the booth. Yes. That's Linux World.
What is the booth?
And are you, the Silicon Valley Linux user group and my group, Earth Treasury, are sharing a booth where we're going to talk about user groups in general and the one laptop per child in particular. So if you want to talk about Baypiggies, you're welcome to join us. What's the dates of Linux World? I'm sorry, yeah, middle of the week.
What day is the Bird of Feather? Are you guys doing it Tuesday or Wednesday?
Tuesday, I believe.
You get one day off from my boss. So.
Yeah, well, then make it that one, sure. Thank you. If anybody wants, you can communicate with me.
More announcements? You're dismissed.